Okay, this question is asking to provide the major products for this reaction between sec-butyl bromide and potassium tert butoxide in tert butanol. So we have this secondary carbon that has a good leaving group, and the reagent here is tert butoxide, and tert butoxide is a very bulky, strong base, and basically anytime you see tert butoxide in an OChem 1 class, you need to think right away that it's probably going to be an E2 reaction, and that's what we're going to have here because it's secondary carbon with a good leaving group and a very strong base. So we have an E2 reaction. So to come up with the products, I'm just going to go through the mechanism. And in E2 reactions, what happens is the base, which in this reaction is tert butoxide, comes in and it takes a proton off of a carbon that's adjacent to the carbon with the leaving group, and at the same time the electrons that were involved in the bond with the proton come down to make a double bond, and then the leaving group is kicked off, and that gives us this as a product. But there's another thing that can happen with this reaction, and that is the tert butoxide can take a proton off of this carbon instead of this carbon, and that actually gives us a different product. So I'm going to draw that mechanism now. And what we have is another E2 reaction. Tert butoxide takes the proton, the electrons come down to make a double bond, and the bromide ion gets kicked off, and that gives us this guy. And what's interesting is we actually get both of these products, but we actually get a little bit more of this guy. So I guess this would be the major product if it's asking for just one, even though I think it would be technically correct to list both of them. But yeah, it's weird that you actually get more of this because this terminal double bond is actually less stable than the more substituted double bond. But the reasoning we get more of it is what's called the Hofmann rule, which is just whenever you have an E2 reaction with a very bulky base, you end up with more of this Hofmann product compared to the other product, which is called the Zaitsev product, which I think can be spelled a couple different ways, but this is one of them. Yeah, and the reasoning for that, like I said, is the bulkiness of the base. The transition state for this mechanism is significantly higher, I guess, enough that it makes a difference because of the steric hindrance of this, the tert butoxide coming in to attack the secondary hydrogen compared to the primary hydrogen. And I guess I can draw a potential energy diagram just to show this. And that would look something like this, which we have our more stable product. But what we actually have is the Hofmann product, which would have a lower activation energy because there's less steric hindrance when you attack the primary proton. But you end up with what's actually a less stable product, which is kind of interesting. So yeah, for this example, you end up with the Hofmann product. And if in this example we weren't using tert butoxide, but we were using another very strong base that isn't especially bulky, you would actually end up with a majority of the Zaitsev product. So I guess the key thing to take away from this example is very bulky bases like tert butoxide give you E2 reactions with Hofmann products.